What's up, people? Block 1, you've already seen this, but block 4, we didn't get to it. So this is a real sort of standard question about an incline. So we have a wagon towed up a hill. We're given an angle of inclination. So we'll start with the free body diagram. All right. Here's what I'll just call mg. Forget about calling it weight. There's our normal. Towed up a hill. Here's our tension force. And let's see. I think it says, yep, neglect friction. So that's our full free body diagram. Right now that we're using axes that are parallel and perpendicular to the direction of motion, let's break our mg up into components. And like we said earlier today, the angle of inclination there is the same as that angle on the top of that triangle. So now this kind of question, notice I haven't really read the question yet. All I've read is the situation, and that's enough to start, right? We know for sure we're going to draw a free body diagram. We know for sure that we're going to do net force statements. I'll go x direction first. So this is going to be T minus, I haven't labeled them, but here's mg parallel, here's mg perpendicular, equals ma. Well, probably now a good time to see what the question actually wants us to find, right? So, how fast is the wagon moving after going 80 meters up the hill? All right, so this is a kinematics question, right? And the connection between this, a dynamics problem, and that, a kinematics problem, is acceleration. All right, so we have to find acceleration in this problem. That's step 1. So let's see. This I'll turn into T minus mg. Well, mg parallel is mg sine theta. Divide by this mass here. That's our acceleration. Okay. So let's see. Calculator. T 140. Oops. Minus 40 times 9.8 times sine 18.5 divided by mass. Yeah, we get an acceleration 0.39 meters per second Okay, with that, going back to kinematic stuff, we're going to say, let's see, starts from rest. V naught is 0. Well, I'll use my A, 0.39 meters per second. We want to know how fast is the wagon moving after going 80 meters. So, come here. Equation V squared V naught squared plus 2A delta X. Well, V, that goes away. 2A delta X. Whoops. Force of habit, Regents, VF. We just call it V. V is times 2 times 80. 7.9 meters per second. Fair enough? That's okay. That's a pretty straightforward one. Now this activity on the next slide, and again, pause if you want, rewind if you want, but hopefully this one's okay. All right. Next slide here is something we're actually going to try to do tomorrow. We're going to try to measure some coefficients of friction, or a couple of them at least. All right. And this is really just showing us how we'll do it. Although this should be a K, you might want to change that now, right? Because we're slipping. Okay, now this one, you know, a good little, I don't know, just look into a couple different situations, especially when we look at friction with these things. So I'm going to, you know, redraw in. Well, here's mg, right? There's the normal. Here's mg perpendicular. Here's mg parallel. Okay, so the question is, if we want there, in this one, if we want there to be no friction at all, right? There's a certain tension force T we can pull with such that friction force is 0, right? Well, that's got to be if, well, actually, we should really point out, if I could even get rid of this. If there's no friction at all, static or kinetic, the only way for that to happen is, well, it can't be moving, obviously, right? And it's got to be in equilibrium, well, due to something else. So in this case, we're going to say that the net force in the x direction is 0, or that T, well, really equals mg parallel. We skip the step saying T minus mg parallel is 0. That's the net force. Well, so that's pretty straightforward. T, in this case, is mg sine theta. If we use g as 10, well, mg is 100. The sine of 30 is a half. Well, that's 50 newtons. Okay? Well, if we pull a little bit harder than that, what's going to happen? So we pull a little bit more than 50 newtons. Well, that's going to make a little bit of static friction force right there. Remember, we said static friction force can vary from 0 up to some maximum value. And let's say when we say a little harder, it's less than that maximum amount of static friction. All right, so we get that little bit of static friction there. We'd still, let's assume that we're still in equilibrium. Now we get T minus mg parallel minus the static frictional force is 0. Well, we'd say that frictional force is T minus mg parallel, or T minus mg sine theta. Okay? Now, it's possible that we could pull a little bit less than 50 newtons, or with a little bit less than 50 newtons of force. And it's possible this thing could still be in equilibrium. Well, the only way for that to happen is if we get a little bit of frictional force this way. Now, what's real important to point out here is I'm not saying that at any instant there will be two different frictional forces acting on this mass. Right? We're trying to use this color coding, meaning that when T is more than 50, this is the force that appears. When T is less than 50, this is the force that appears. They will not act simultaneously. It will be one or the other, depending on how hard we pull. Okay, so in this case, our net force statement changes just a little bit. Now it's T minus mg parallel plus the force of static friction equals 0. So that says that the frictional force in this case is mg parallel minus T, or is mg sine theta minus T. Fair enough? All right, just a couple different looks. Friction can, especially static friction, can bring some pretty unique phenomena, so worth taking a little look there. Yeah, now this one. Hey.
Hi, how's it going today?
Fine.
Yeah, I thought it was your USB. Can I take the...
I'm recording this right now, so can you come back?
Sorry.
That's okay, that's okay. So let's do a coefficient of friction problem. All right, great problems here. And again, we'll look at we'll do a little activity where we calculate some coefficient of friction. All right, so find the coefficient of static friction needed to keep the system at rest. All right, well, here's where I would start. We have our object here, M1G, right? Normal force. Here's a tension force. And I guess what we're saying is, it's hard to tell right now what direction the mass, or sorry, what direction the friction force has to act. All right. But what we can tell is if this system is at rest, if we look at M2, we have M2G and tension. Okay. Well, this says, again, if it's at rest, net force is 0, T equals M2G. Straightforward. Boom. Let's just call it, we'll say G is 10. T is 100 newtons. Right? Okay. Now over here, if we do this and say M1G parallel, M1G perpendicular, well, I don't really advocate doing it this way, I guess, but it's worth pointing out, this thing's also a 10 kilogram mass. So here's, mg is 10 kilograms, and the angle's 30. You should prove to yourself that that's 50. All right? Well, maybe I'll help you. M1g sine theta is 100 times the sine of 30, which is a half. Yeah, that's 50 newtons. All right? So we have 100 newtons here. We have 50 newtons pulling down the hill. That means there must be another frictional force pulling down the hill of 50 newtons. All right, and really what, the right way to do that is this, and then we'd say T minus mg parallel minus the friction force is 0. And we'd say that the friction force is T minus mg parallel, or T minus mg sine theta. All right, and that's, yes, that will get you the 50 newtons. Right? If you were trying to just pick a direction for F, you can just pick one. If you get a negative answer, then it means the direction you picked F to be in is the wrong way. All right? If you ever solve for a force and you get a negative answer, it means that the direction you picked is the wrong direction. Okay? Since our force of friction comes out positive, it means, yes, that's the right direction for the force of friction. Okay? Now, we want the coefficient of static friction, all right? Or the coefficient of friction. So, really what we're trying to do now is do something with this. F, really that the incline exerts on 1 is mu times the normal that the incline exerts on 1. Well, we already know what the force of friction is. It's 50 newtons. We have to figure out what the normal is. So that's a net force in the y direction is 0. So if we look at our free body diagram for object 1, we have n, again, I'll do n that the incline exerts on 1, minus mg perpendicular is 0. Or n, incline on 1, is mg, I'll skip a step, cosine theta. I believe that's about 87. I think the cosine of 60 is 0.866. I mean cosine of 30. Yeah, 0.866. So we'll call that 87. Again, using G is 10 here. All right, so we have normal. We have friction. So mu equals friction force, normal on 1, divided by normal force, normal on 1. Oh, that's about, I don't know, I got force of 50 divided by 87. Yeah, 0.57. Okay? What do you think? Fair enough? Ooh, now I think this one, that one's a little different. This one's different also. We did that one. Let's see. Yeah, okay, so we're in a good spot. This one's a good one to add on to your homework, to tell you the truth. Okay? So why don't we, yeah, we're going to add that one onto your homework. The hard one on the bottom of the page on that inclines problems, on that incline problems sheet, you could probably hold off on that. I mean, you try it if you want, but it's not one that I'll require. Let's do 1 and 57 and 50 and this one. Okay? This one's probably a tricky one too. So we'll see you tomorrow, folks. Have a good one. Oh, and there's another video up that's the solution to the quiz, the multiple math systems quiz, if you want to watch that. Okay? See you guys.